So good morning, everyone. Last week we talked about uh, uh, quantitative analysis. We define quantitative analysis. We will talk about the instruments or the apparatus that is being used during quantitative analysis and precautions that must be taken during titration. I will talk about indicators and the choice of an indicator that is being used during titration. Now today we are going to concentrate on calculation, okay, and under this calculation some interesting formula are going to be given to you which will help you and will guide you on how to go about this calculation. And in this quantitative analysis, three calculations are very important. Firstly, we tend to standardize a particular, because in volumetric analysis titration, two solutions will be given to you. Standard solution, the one in which the concentration is known, and the second one which we are going to standardize, we are going to look for its concentration. So in this calculation, we tend to determine the molar concentration, we tend to determine the mass concentration. Also in this calculation, you can also determine the purity of a substance, whether a particular substance is pure or not. You can determine percentage purity, percentage impurity. Also, you also determine water of crystallization, and you then look at acid-base titration, as we will further explain. Look at this calculation in detail. Calculation in volumetric analysis. So, the volumetric analysis is used. The usefulness of the calculation or the volumetric analysis. It is used to standardize unknown solution. You are going to be given two solutions. One of them will be standard solution, and the standard solution is a solution in which the concentration is accurately known. So it is used to standardize an unknown solution. The other solution you will be required to calculate its concentration. That is the unknown solution that you need to standardize. Two, you use volumetric analysis to determine the purity of the substances. Whether a substance is pure or not, you will have to calculate percentage purity, percentage impurity. Third one, you use volumetric analysis to calculate molar mass, molar concentration, mass concentration, number of ions, particles, water of crystallization, and solubility products. These are what we can use volumetric analysis to determine or to calculate a given reaction. So now, as I've said, a standard solution is a solution in which the concentration is accurately known, because in the experimental procedure, in the reaction, you'll be given two solutions. As I've said, one can be A, acid, the other one can be B, base, and one of the two solutions will be standard solution, in which the concentration is known, and you'll be required to find the concentration of the other solution. So that means in a volumetric analysis, you must, a particular solution must be a standard solution. So now, what are the formulae? What are the formula that you must put at the back of your mind before you go into this calculation? The first important calculation is how to know our formula for molar concentration. Molar concentration is equal to her mass over volume in dm³, provided the volume is given in dm³. But if the volume is given in cm³, that means molar concentration will be equal to what? Number of mole over volume in cm³ times 1000 over 1. And also the second equation is mass concentration. The molar concentration is, the unit for molar concentration is mole per dm³, while the unit of mass concentration is gram per dm³. So the formula for mass concentration is mass in gram over volume in dm³. But if the volume is not given in dm³ also, that means the formula to be used is mass concentration over mass is equal to mass divided by volume in cm³ times 1000 over 1. So if the volume is not given in dm³, it is given in cm³, you have to convert the volume in cm³ to dm³ by dividing with 1000. So there's a formula that connected relationship between molar concentration and mass concentration. And the formula is molar concentration is equal to mass concentration over molar mass. When you know the name of a particular compound, automatically you have known the molar mass. For instance, if the compound is sodium chloride, the molar mass of sodium chloride will be what? Sodium is 23 and chlorine is 35.5. From there, you add together and you get the molar mass of the compound. So this is a relationship that links molar concentration to mass concentration and molar mass of a particular compound. So having understood that, the formula still continues. In a titration, we have the standard formula to be used is CAVA divided by CBVB is equal to NA over NB. What are these parameters mean? Ca is the concentration of acid. I have told you they are going to be given two solutions. A will be acid, B will be base. So Ca means concentration of acid in mole per dm³. Va means volume of acid, and Cb is concentration of base in mole per dm³. Vb is volume of base in cm³. Na is number of moles of acid, while Mb is number of moles of base. So these are equations that are going to be used in calculation of acid-base reaction. So now let us look at how to get mole ratio. How can we calculate our Na and our Nb? Now the Na and Nb can only be calculated, can only be gotten from the equation of reaction after the equation has been balanced. For instance, if hydrochloric acid reacted with sodium hydroxide to give sodium chloride plus water. Now, the number of moles of acid there is 1, because there is no, the 1 is serving has a numerical coefficient of HCl, and in chemistry we don't normally write 1, we leave it like that. That shows that the Na, number of moles of acid, is 1, and the base is sodium hydroxide. There is no number before it. That automatically proves that 1 is before it. So the number of moles of base is also 1. If we look at the second equation, where tetrasulfuric acid reacts with sodium hydroxide to give sodium sulfate plus water, this is a neutralization reaction. Now, the number of moles of acid in this case is 1, and number of base, if you look at sodium hydroxide, the number before it, that is the coefficient, is what? Is 2. That shows that number of base is 2. So Na and Nb can only be gotten from the equation of reaction after the equation has been balanced. So, having understood how to calculate Na and Nb, let's give a particular example to see how we can relate those formulas given above in terms of calculation. Look at this example. Now, this is a standard-wise question. We are given that A is an acid. A is 0.05 mole per dm³ of H2SO4. B is sodium trihydrocarbonate 4 solution. If 35.5 cm³ of acid was required to neutralize 25 cm³ of the trihydrocarbonate 4, calculate A, concentration of B in mole per dm³, concentration of B in gram per dm³, volume of carbon 4 oxide liberated at STP during the titration. And in this question, you are already been given a balanced equation where tetrasulfuric acid reacts with sodium carbonate to give sodium sulfate plus water, and carbon 4 oxide is liberated. Now, if you look at this question very well, Ca has been given to be 0.05 mole per dm³. Now, Cb is unknown, and that is what we are required to calculate. Va has been given to be 34.5 cm³, and Vb has been given to be what? 25 cm³. Now, from the equation of reaction, we can get our Na and Nb. From this particular equation, Na is 1 and Nb is also 1. From here, you apply your formula that says CAVA over CBVB is equal to Na over Nb. From there, you input your value. Ca is 0.05 times 35.5 divided by Cb, which you have to calculate for in the first question, times 25, that is volume of base, is equal to 1 over 1. That is the mole ratio from the equation of reaction. When you do the calculation using a calculator, you are going to get Cb, concentration of base in mole per dm³ now be 0.075 mole per dm³. Now, let us now look at the second question. You have to calculate concentration of B in gram per dm³. Now, you already calculated concentration of B in mole per dm³. You are now asked to calculate concentration of B in gram per dm³. It's very easy. You apply an interesting equation that says concentration in mole per dm³ of B is equal to concentration in gram per dm³ of B over molar mass. The compound you are working with is sodium carbonate. You find the molar mass of sodium carbonate. Sodium is 23. That is 2 times 23 plus carbon is 12 plus O3. Oxygen is 3. 3 bracket times 16, and when you add everything, you multiply. We are going to get the molar mass of sodium carbonate to be 106 gram per mole. From this, I can now state that you can calculate your concentration of B in gram per dNq. Apply the formula that said concentration of B in gram per dNq is equal to concentration of B in mole per dNq times molar mass of B. So from there, the concentration of B in mole per dNq that you have calculated above is 0.075 mole per dNq times molar mass that of B that you just calculated is equal to times 106 gram per mole. When you multiply the two, you are going to get the concentration of B in gram per dNq to be 7.95 gram per dMq. That's a very simple calculation. Last one, you have to calculate the volume of carbon 4 that liberated as STP. You go back to the reaction. Sodium carbonate give us carbon 4 oxide at the product side. From the equation, we look at 1 mole of sodium carbonate from the equation is equal to 22.4 dNq of carbon 4 oxide. You remember that 1 mole of any gas or 1 mole of any substance will produce 22.4 dNq of the gas at STP. So 1 mole of sodium carbonate will produce 22.4 dNq of carbon 4 oxide, and 0.05 moles from the concentration we have calculated for sodium carbonate. So 0.075 moles of sodium carbonate will give us X. Then you multiply, and that will give us 0.075 times 22.4 dNq divided by 1, and the final answer volume of CO2 liberated as STP will now be equal to 1.68 dNq of carbon 2 oxide liberated. That's a simple question and an illustration on how to go about calculation in volumetric analysis. Now, let us now look at calculation under purity of substances. Volumetric analysis is often used to determine the purity of substances, usually expressed as percentage. Yes, I've told you initially that we use volumetric analysis to determine if a substance is pure or impure. But you must put at the back of your mind, when a reaction occurs, you are only working with a pure substance. Okay, you are only calculating with a pure. The reaction of acid with base are pure. Okay, so let's say a particular calculation to illustrate that. Now look at this example. 12 grams of a mixture of anhydrous sodium tricarbonate 4 and sodium chloride were made up to 1 dNq of aqueous solution. That means that this sodium carbonate is the base in this question, and the impurity there is sodium chloride. So when sodium chloride are mixed with sodium carbonate, 12 grams of the mixture was obtained. Now 25 cm of this mixture were neutralized by 20 cm of 0.2 molar of hydrochloric acid. So now we are now have to calculate the mass of the sodium chloride impurity, the percentage purity of the tricarbonate 4 salt, and the impurity of the tricarbonate 4 sample. And we are given that sodium carbonate, the molar mass of sodium carbonate is 106, while that of hydrochloric acid is 35.5. Now, from this question, you tend to write the equation of reaction. The equation of reaction, the reaction is between sodium carbonate and HCl to give sodium chloride, water, and liberate carbon 4 oxide. From the equation of reaction, we tend to get the mole ratio. Number of mole of base is 1 from the equation, and number of mole of acid is 2. By applying the formula, it says CAV CVVB equal to Na over NB, and we are asked to calculate the molar concentration of the base, of the pure base. And when you substitute your value, the concentration of acid is 0.2 times volume of acid is 20 divided by CB, that is the concentration of the base, times VB, volume of base, which is 35, is equal to number of mole of acid to number of mole of base 1. When you multiply and make CB the formula, you multiply your result. You are going to have the concentration of base in mole per dNq to be 0.08 mole per dNq. That concentration is concentration of a pure base, pure sodium carbonate in the reaction. So now the second question asks us that we calculate percentage purity of sodium carbonate sample. Now you are going to convert the molar concentration of sodium carbonate to its mass concentration, and we know that the molar mass of sodium carbonate has already been given together to be 106. So molar mass of sodium carbonate is 106. Molar concentration of sodium carbonate is equal to molar mass or mass concentration of sodium carbonate is equal to molar con times molar mass. So by finding mass concentration of sodium carbonate, we have 0.08 mole per dNK times 106. Then mass concentration of sodium carbonate will give us 8.48 gram per dNK. That mass we just got is the pure mass of sodium carbonate. So we are now have to calculate percentage purity of sodium carbonate in the sample, which is equal to mass of pure sample divided by total mass of sample times 100/1. So the percentage purity will be equal to the mass of pure sample, the one we just calculated, is equal to 8.48 divided by total mass of samples that was given from the question, that when you have sodium carbonate for ACS, the total mass is 12. So that is the total mass of sample, which is divided by 12 times 100/1. At the end, you get that percentage purity of sodium carbonate in the sample will be what? 70.7%. Now, the last question, we want to get the percentage impurity of sodium carbonate sample. Since you have gotten percentage purity, okay, to get percentage impurity is very simple. Just subtract it from 100, because the total must be 100. So percentage impurity of sodium carbonate is equal to 100 minus percentage purity. That means 100 minus percentage purity we just calculated in question B, that is 70.7, and the percentage impurity of sodium carbonate to the sample is 29.3, and that is the end of the topic. In my subsequent class, my next class, we are going to look at how to calculate water crystallization, and also look at acid-base calculation, acid-base reaction. Thanks.